Okay, welcome back. Happy Monday. Today is September 22nd. We talk about something called lines of best fit. Next class, in context linear problems, which you can translate to word problems. That's what next class is about. Friday is essentially a catch-up day or a review day in preparation for our very next quest, which is coming up 1 week from today. Any questions on the calendar? As usual, there are practice problems for that quest inside the packet. Look around and you will find them. There are also videos on YouTube of me going through those problems. Okay, we'll start at the top of page 41. It says, today's class we examine plots of real-life data and explore how to use the line of best fit. Number one says the demo is long, so I'm going to try to just sort of pick and choose what we talk about together. You can read some more of the details later. I'm not going to gloss over any of the math, but there's a lot of text in here, and I think I shouldn't have written so much stuff. So first thing to do is take a look at number 3 here. It says in 1982, drunk drivers were responsible for 25,165 deaths in car accidents, which was 57.3% of all fatalities due to car accidents. And so looking at this chart, you can see the first row says exactly what we just read. 1982, 57% of all car-related deaths were also alcohol-related. And we've got a bunch of other data in this chart, and you can see as time passes in the first column what appears to be happening to the percent of fatalities that are alcohol-related. It's going down. Seems like we can say that by looking at these numbers. If you wanted to, you could start subtracting to try to figure out like what it's going down by each year. So in this first one, it went down by 6%, and this next one 1%, and the next one 3%. So it doesn't appear to be going down by a consistent amount, but down seems to be the trend. But it's kind of hard to say more than that by just looking at a table. You really have to do some calculations to try to figure out what's going on. But instead, what we'll do is take a look at something called the scatter plot, which is just a graph of a bunch of data points. And so if we look down here at this picture, we see our very first scatter plot. And the information in this graph is supposed to capture everything that's in that table. So for example, if we look at the first row in the table, it says 1982, 57%, and you're supposed to see that in this leftmost dot. This one somehow is supposed to represent 1982 and 57%. So hopefully we can see the 57 is the y coordinate, right? That's our percent due to fatalities. And then 1982, if you just read that as a number, not as a year, how would you read that out loud? 1,982, right? And so if you wanted to graph this and actually treat it like 1,982, you'd be graphing way to the right on this horizontal axis. So instead we do something very common, and that's to rescale. And so instead of 1,982, we're just going to say 2. But it's important to make sure that we've defined that. I think we have right up here, let's see, T years since 1980. So 0 is now 1980, 2 is 1982, etc. Okay, so what we're going to do first is fill in the blanks for points A and B. So point A is pretty easy to read off the graph. What are the coordinates of point A? 8 and 50, that's easy enough. What does that really mean in terms of this scenario? What does the 8 mean? 8 years after 1980, which means 1988. What does the 50 mean? It's 50 what? 50% of car-related deaths were actually alcohol-related. Okay, and do you see that in the chart, 1988, 50? Okay. And then point B, we do the same thing, but it's tougher with point B because point B is not like on the background grid. So, I mean, I guess I could estimate and say this is probably a 19. I'd have a harder time estimating over here, 36, 37, 38, I don't know. But yeah, but you have the chart, so read it off of the chart. So from the chart, you see a point that says 19 what? 99, and what was the percentage at that time? 37, and so that must be our point, 19, 37. Okay, so again, that's called the scatter plot. It's just a visual representation of the data from the chart. And do you see the decreasing trend looking at the scatter plot, looking at these dots? Yeah, we can see the dots are getting closer and closer to the horizontal axis. And we can also see that it's not a perfect straight line. If it were a perfect straight line, then these red numbers would have all been the same. We would have decreased by the same exact amount year after year. And you can see that it doesn't decrease by exactly the same amount year after year. But what we can do is down here in part C, it says sketch a line that you think fits the data the best. So see if you can use a straight edge if possible. You can use the yellow folder maybe or your book, and you're just going to draw a line that you think fits the data the best. Now I caution you, the goal is not to connect two dots with a straight line. You should not be connecting two dots with a straight line. You should be drawing a line that you think gets pretty close to as many dots as possible. Now, admittedly, this is a really wishy-washy set of instructions I'm giving you in a math class. But you go ahead and draw your straight line, and you try to get as close to all the dots as you possibly can. Yeah, it's got to be a straight line. So I've got my line up here. Is this going to be the same as your line? No, we all just drew different lines. But the idea is you're not connecting two of these dots. You're just trying to look at all the dots and draw something that's close to all of them. Let's move to the next page. And we will see the actual best line is this one right here that's drawn. So hopefully we drew something that was kind of close to that. Does this line actually hit any of those data points? Not exactly. I mean, I guess it's pretty close to this one over here, but you know, I mean, like that dot right there is much bigger than it is in reality, right? It's supposed to be just this like little teeny tiny infinitesimally small thing. So the line doesn't hit any of the data, but it is as close as possible to all of the data. Now, as close as possible is another wishy-washy thing for a math class. And so I'll just say that at this stage, it's beyond the scope of our course to talk about what it means to say as close as possible. But if you take a statistics course, you will learn exactly what that means. And that line is the only line that is the best one of all the lines. Calculators and computers can find it, but when you're doing homework tonight, I think this is written down here, we're just going to be approximating the line of best fit, okay? So expect that you're going to get slightly different answers from the answer key and slightly different answers from each other because you're just drawing your best estimate without technology. Okay, so let's move to part B. It says we can use this line, the line that's drawn up there, to make predictions about the data. Let's use the line to predict the percent of fatalities due to drunk driving in 1993. Now, 1993 corresponds to what value on our horizontal axis? Is it 3? Or is it 13? It's 13, right? 1980 was our 0. So t equals 13. Is there a dot at t equals 13? No. So this is information that we do not have from the table. But we can go to our line at t equals 13. And once we've got our dot, what should we do next? How do we answer this problem which says estimate the percent fatalities in 1993? Estimate what from the graph? Yeah, let's estimate the y value. So just take this dot and come right over here and land on some y value which you estimate. So what does it look like? 43, 44, 42 is probably okay. Anything we do here is estimating. So our estimate, I'll say about 43, which means that our estimate is that in 1993, about 43% of car-related deaths were due to drunk driving. Again, we don't have a data point there, So we can't compare to any known value, but this is our best guess for the reality back in 1993. Okay, so now we're going to do some stuff that looks familiar, things that we've done this semester already. So what we're going to do is part C. Use the graph of the line to pick 2 points on the line that have, quote, nice coordinates. We're picking 2 points on the line. We are not picking 2 data points, although if one of them happens to be on the line, that's fine. But you are not picking data points here. You are picking 2 points that are on the line. So, unfortunately, there aren't a whole lot of nice points that are on the line. I can find 1 point that is almost perfectly on this line that's also on the background grid. Do you guys see it? Yeah, it's at, where is it? Which one? Yeah, for me, this is the one my eyes went to. And yeah, 850 is okay. That's not bad. I mean, the dot is at 850 and the line is a little below it, but we're going to be estimating no matter what. So if we want to use those 2 points, that's fine. Let's go ahead and let's use those two. So the first one here is 16, 40, and the other one 850. That's fine. Neither one of them is perfect, so don't worry about the fact that that line doesn't exactly hit the background grid. But now that we have 2 points on a line, we can find the equation of that line. And that's what we're going to do. So this is something that should start to look familiar to us. So let's write down in here in part C, the same points that we just wrote up above. What were they? 8 and 50 and 16, 40. Okay, so let's find the equation of the regression line. That's the line that's drawn on that grid, and it's the line that you estimated when you drew on the previous page. Step 1, got to find the slope if you're going to find the equation of a line. So typically slope is change in y over change in x. Right? Are we getting familiar with that triangle symbol? Greek delta, change in. Okay, but we don't have the letters y and x in this problem. We have t and p in some order. T stood for, in the problem, what does t stand for? Time, and p stands for percentage. Okay, so that's why t and p are chosen, but now we got to put them in the right spots. Which one is like our new y? Is the p. So we'll put p right up there, and then t right down there, okay? Just have to replace them with the normal x and, replace the normal x and y with t and p. Okay, so let's start calculating. So change in p, what I'm supposed to do is take the p values, the second numbers, and we'll do what with them? Subtract them, so we'll do 50 minus 40, say. And then downstairs, 8 minus 16, that's the right order. As soon as you commit to an order on top, you got to stay with that same order on the bottom. All right, so upstairs we got a 10, downstairs negative 8. So altogether, what is that? Negative 1.25? We don't have to leave it as a fraction. You can leave it as a fraction. Often for word problems, percentages, decimals are more easily understood than fractions. But either way is okay. And it says here include units, so let's go ahead and add some units in. The 50 and the 40, what were the units for those guys? Those were percentages. The 8 and the 16 were years. It was time, and it was measured in years, right? And so when we talk about this negative 1.25, that's negative 1.25% per year. Some of you might already be thinking about, well, what does that really mean in the scheme of this problem? I think we'll answer that question. Okay, let's move to the next page when we're ready. Step 2 is a big one. It just says find the equation of the line. And it also says use the letters t and p instead of x and y. So let's try to get a little bit out of our comfort zone. Y equals mx plus b is our normal equation, but it's not that big a deal to use different letters, so let's try it. Instead of y, what did we have? We had p equals m, and then instead of x, it's t plus b, so that's our new equation of the line. Okay, so there was a whole big process involved here. Some of you probably should still be doing a lot of the details. We're going to speed this up a little bit, but let's replace the m with the slope that we just found. Minus 1.25, and then there's a t plus b. We found the slope on the previous page. Make sure you're careful with your t's and plus signs. A lot of problems involve t's. There are plenty of good reasons to lose points on a math test, but misreading your own handwriting is not one of them. Okay, next thing to do is to change the p and the t to numbers. And you can pick any point you have. We have 2 points. Let me just write one of them up here. What did we have? 16 went with 40. Okay, so let's plug those guys in. T was first, P was second. So instead of this P equals, what do we have? 40 equals negative 1.25 times, instead of T, 16. And then plus the B, which we're about to find. Okay, so we do that multiplication there. Is that negative 20? I got 40 equals negative 20 plus B. It's just multiplying. Again, the goal was to solve for B, so what should we do to both sides? Add the 20. So we get B equals 60. Yeah, that's exactly right. I'm going to write that in just a second. Let's put this and this together to get our final equation here. P equals negative 1.25 T plus 60. So really the only new thing in this process was that we changed the X and the Y to T and P. But you guys have a lot of practice already. In fact, some last night with your homework, taking 2 points and finding the equation of the line. So if you remove the context of drunk driving and fatalities, this is a very standard looking problem for you guys now. Take 2 points and write the equation of a line. Okay, so that right there, I'm not going to copy it again, but that's the regression equation. And in step 4 here, it says we can figure out how accurate we were, because I actually did this problem on GeoGebra. It's a free piece of math software. Yeah, Cody. Yeah, step 3 is just asking you to write your final answer in one nice place. Yeah. So it turns out the actual equation of the line that was graphed on the previous page was y equals negative 1.19x plus 58.63. So we had negative 1.25. What should we have had? Negative 1.19. Is it close enough? Yeah, I guess. I mean, we estimated points on the line, and neither of them were actually perfectly on the line. So of course there's some error involved. We got 60. What should we have gotten? 58.63. It's close enough. Right? Again, expect that your answers will not perfectly match the answer key when you do tonight's homework. Okay, Sam, what did you say about this 60 business? In 1980, 60% fatalities were due to drunk driving. Somebody, not Sam, where did 1980 come from? There's just one number there, 60. It's our starting point. Okay. t equals 0, that's what the y-intercept means, is what's going on when t is equal to 0, and that was 1980. Okay, so that's the explanation for the 60. This negative 1.25 also has a meaning. So let's fill it in down here. So the slope was negative 1.25. But let's copy the units. We wrote them on the previous page. What were the units on this one? Percent per year. So let's see if we can write a sentence in plain English that interprets that number. So as the years pass, what is this 1.25%? Fatality rate went down. Why are you using down? This is negative, right? This represents a change in percentage every year. A change by negative 1.25% per year. Typically don't say things changed by negative amounts, they just say they decreased. So that's our sentence, something like this. Let's see, percent fatalities decreased by 1.25% per year. And again, your sentence doesn't have to be word for word like this, but it better say something about percent per year to indicate you understand what that means. Okay, and then F says use your regression line to predict the percent fatalities in 1993. Okay, let's try this. Did we answer this problem already? How did we answer this problem on the previous page, 1993? We estimated from the graph. We put a dot on the line at 1993, and then we went straight to the left and we estimated. What was our answer? 43%. Okay, so now what we're going to do is use our equation to try to answer that same problem. So again, the equation, I'll copy it from up here, but the equation is P equals negative 1.25 T plus 60. And when we say 1993, we're really saying something about which variable, P or T. That's T, and what is T? 13. So this problem is really just saying, take the equation that you worked so hard to get and substitute 13 for that T. So P equals negative 1.25 times 13 plus the 60. So what do we get? Is that 37.75? 36.75. 43.75. Sounds good. 43.75. What did we say from the graph? 43. Close enough. Again, I mean, we're estimating all over the place. So do not expect like any kind of consistency in your answers. Okay, let's do the same thing, but for 2002. Using the equation, not the graph, but the equation. Yeah, so 2002 is really 22 for us, right? 1980 was the 0 mark. So that means that 22 goes in there. And 32.5. Is that right or is that wrong? Okay. All right, so last thing is two real quick vocabulary words. When we did 1993, would you guys agree that even though it wasn't in the table, it was between the highest and the earliest and latest values in the table? The table started in 1982 and ended in, what's the last year in the table? 2000. So we've got a number, 1993, that's in between the start and the end, right? And when you are in between, the word we use is interpolation. Inter means between, right? But 2002 was beyond the scope of our table, right? It was after the table ended. And when you are after, you're outside of the range, then that is called extrapolation. I'll use a different color here. So when we did 1993, it was called interpolation, 2002 extrapolation. Collating, I don't know. I guess probably that's still internal, as long as you're still within the time range. One of these is more risky than the other in terms of putting your faith in the calculation. That's the extrapolation. It is very, very risky to extrapolate. It's something we do all the time, and if you read just about any newspaper article with a number in it, there's going to be extrapolation involved. It's people making their best guess, assuming that things continue just like they have been. But that's not always the case. So again, extrapolation is riskier in terms of putting faith in the outcome. Neither one of them is going to give you perfect answers, but interpolation is probably more reasonable to believe in numbers that are between the range as opposed to using something to predict perhaps far into the future. Okay, so the activities are not actually in the packet, but they're in the textbook. So hopefully there are a few copies of the textbook on every table. If not, let me know. But you're going to try these two exercises. And if you finish both of those, then get a jump start on the homework.